Welcome to the ChemDoctor, and in this presentation what I want to do is offer the viewer more practice in writing what are called ionization equations. Now, an ionization chemical equation follows all of the rules of a standard chemical equation, meaning that it has to be a balanced equation. We're going to be using arrows to show, or an arrow to show transitions, and so on. Now, there are four things that the viewer needs to make sure that they know before they dive into this video. All right, the first is that you need to make sure that you have a strong knowledge of the elemental ions. All right, and these would be the ions that generally form in group 1A and group 2A metals. For example, the group 1As are the +1 metals when they ionize, group 2A the +2 metals when they ionize, and then group 5 of the nonmetals, the group 5A, which for our purposes goes to -3, the group 6A, which goes to -2, and the group 7A, which goes to -1. All right. So you need to make sure that you know your elemental ions. And if you're in a new chemistry class, like you're new to this stuff, I hate to say this, but you probably need to memorize that material. And I offer other videos on my website and on my YouTube channel that emphasize this area. If you've got experience, then maybe perhaps this is not an issue for you. The second thing is you've got to make sure that you know your polyanions. All right, and when I say know the polyanions, there's approximately 24 of them. There's more when you consider families, things like phosphate versus phosphite. You need to know formula and charge. And the reason this is important will be because we're going to be dealing with ionic compounds that we have to split or that we have to ionize into their constituent ions. And when you're dealing with transition metals, and I will show you some examples of that, the only way you can figure out the charge on the transition metal is by knowing the anion. All right. The third thing is that you need to remember that's very important. What I call the law of electrical neutrality. And the idea here is that when you're dealing with an ionic compound, you need to understand that the sum of charges for the cation plus the sum of the charges for the anion have to equal 0. So that's an important concept, because when you take the ionic compound and you split it up, you need to make sure that you split it up into the right number of each type of ion. Generally speaking, this is given from the subscripts that appear in the chemical formula, and we will practice this. All right, and then the fourth thing is that you need to make sure to apply the law of conservation of mass. And what that says, or how we state that relative to a balanced chemical equation, is that you need to remember that you must have the same types and numbers of atoms on both sides of the arrow. All right, so these are the four sort of knowledge-based things you need to make sure that you know going into the material I have on my website and the YouTube channel when dealing with ionization equations, or really any of the stuff that involves ionic compounds. So let's start with what I consider a simple example. So what we're going to do is write the ionization equation for sodium bromide. Now, in order to do that, what you need to realize is that, okay, first off, if you look at this formula, you can see that the element sodium, well, it's actually sodium ion, and bromide are paired 1 to 1. So what that means is that the magnitude of their charge has to be the same but opposite. All right. Now, how do we figure out what this is? Well, this comes back to my point about knowing your elemental ions. See, sodium here is out of group 1A. I'll write that up here. So we know that it's going to be +1. And, bromide is out of group 7. So it is equal to -1. So I'll put a little arrow here. This is out of group 7A, and therefore the charge on it is going to be -1. So the sodium is +1, the bromide is going to be -1. So when we go to write our balanced ionization equation, here's what it's going to look like. We write the NaBr. Okay, then we use an arrow, which means to form. And by the way, I'm using a term, I'm saying we're writing the ionization equation, right? Ionization equation. The word ionization means to form ions, right? To form ions. And it's worth mentioning that the reason that this is important is because in more advanced classes of chemistry, like advanced placement chemistry or university level general chemistry, university analytical chemistry, and also university physical chemistry, you deal with solubility equilibriums, and these are equilibriums that involve salts. Remember, that's what this is. It's a salt that are sparingly soluble in water. So you have to be able to write a valid ionization equation. So getting back to this, the ionization equation for this one will look like this. We'll have Na plus Br minus. All right, and we see when we look at this relative to the law of conservation of mass that we have the same numbers and types of atoms on both sides of the arrow. All right, let's try another example. This one is a little bit more complicated because you can see that the anion in the formula has a subscript of 2. That means that there are 2 Cl's or 2 chlorides in this compound that are paired with 1 atom of calcium ion. All right, so remember, these are ionic compounds. That means that they're composed of cation and anion together. The cation is the positive charge, the anion has the negative charge. All right, now to remind you again about the importance of background, all right, we know calcium's out of group 2A. So that means it has a charge of +2 on it. And again, the chloride shares the same family or group as bromide, so its charge is going to be -1. And as you see from the subscript, there's 2 of them. So now when we go ahead and we're going to write the ionization equation, that's going to look like the following. All right, so we're going to rewrite the CaCl2. We use an arrow to indicate that this is now going to ionize. It's going to change its form to ions, free ions. It's going to be Ca +2 plus 2Cl minus. So note that the subscript here becomes the coefficient in the balanced equation. And in fact, we have met the law of conservation of mass because there's 2 Cl's here and there's 2 of them here. All right, so let's look at another example. In this one, yet again, it'll be more complex. We have Mg with a subscript 3 and then nitride with the subscript 2. All right, now we need to split this up, and you can see already, if you understand your chemical formulas, that there are 3 Mgs and that there are 2 nitrogens. All right, and what we need to do now is establish the oxidation state. Now see, I used another word there. So oxidation state is just another way of using the term charge. All right, so for the magnesium, we know it's out of group 2. All right, so it's going to be carrying a charge that's +2, and nitride is out of group 5A. In this case, it's going to be -3. All right, so let's go ahead and write the ionization equation for this. We rewrite the formula. We use an arrow. There's going to be 3 Mg plus 2s, like that, plus 2 N minus 3s. All right. And you can see that we've got 3 Mgs on this side, 3 Mgs here. We've got 2 nitrogens here and 2 nitrogens here. Very quickly, if you look at the coefficient multiplied by the charge on the nitrogen, that gives us a total of -6. When you look at the coefficient for magnesium ion times +2, we get +6. You add these two things together and you get 0, which gets us back to the electrical neutrality of the formula right here. All right. Okay, let's look at another example. In this one, we're going to now bring in the polyanions. All right, so in this case, we're going to write the ionization equation for sodium carbonate. And again, your knowledge, here's where we're bringing in number 2 in my list. The sodium is out of group 1, so we know it's +1. When it ionizes, when it loses electrons, when it was combined with the carbonate to form carbonate, whatever the situation was that led to the compound, all right? And the carbonate is a polyanion whose formula is CO3 and its charge is -2. All right, so, and you can see that from the formula, since we know unambiguously what the charge is on the sodium, and the fact is there's 2 of them. The electrical neutrality argument means that the carbonate itself had to have a charge of -2. So let's go ahead and write the ionization equation. All right, we rewrite the formula like this. We have our arrow. There are 2 sodiums, so it'll be 2 Na+, and then there's 1 carbonate, which is CO3 -2. And again, using the same argument that we did for the magnesium nitride, you can see that 2 times +1 is +2. There's a 1 in front of the carbonate, so this is -2. The sum total is 0, and that gets us back to the original formula, the electrical neutrality argument. All right, now let's look at another example that has a transition metal in it. Okay, paired with another polyanion. Now, the reason these guys can be tricky is because copper actually, and I'm going to put this over here, copper can actually be Cu+ usually, or Cu+2. So how do we figure out which oxidation state or what the charge is on copper when it's in a compound? Well, the way that you do that is you've got to know your polyanion, all right, which is right here. And the sulfate has a formula which is SO4, and its charge is -2. So the law of electrical neutrality says is that whatever the copper is, it has to match up exactly with the charge on this in order to maintain electrical neutrality, and therefore the copper in this case has to be +2. So now we can write the ionization equation. It will be copper sulfate, copper 2 sulfate actually, with an arrow, and then we're going to have Cu+2 plus SO4 -2. And these 2 guys combine directly to cancel the charges, which gets us back to the copper sulfate. All right, now let's look at one more example. We have, in this case, magnesium hydroxide. And again, we apply knowledge here. We know that magnesium's out of group 2, so it has to be +2. This is a good example because we've got another polyanion whose name is hydroxide. All right, and it's inside of parentheses with a subscript right here that says 2. So what that means is that you've got 2 OHs inside this parentheses that are paired with the magnesium. All right, so to write the ionization equation, this is what this is going to look like. All right, we rewrite the compound, and then we're going to have Mg+2 plus 2OH minus. Now, very quickly, if we go back and review the idea of electrical neutrality, we see that we've got +2 for the magnesium, and then each hydroxide is worth -1, and there's 2 of them, so it's going to be plus -2, which is equal to 0, and that gets us back to the original compound here. All right, and the law of conservation of mass, we have 1 magnesium here, 1 magnesium here. We've got 2 hydroxides on the right side, and we've got 2 of them over here. All right, so with that, I'm going to go ahead and close this video on writing ionization equations.